In this screencast, I present another proof to the theorem that every natural number greater than 1 has a prime factor. So to start with, we state the theorem. Every natural number greater than 1 is divisible by some prime number. In more mathematical notation, n, which is an element of the natural numbers, and n is greater than 1, then there exists ni, which is an element of the natural numbers, such that ni is prime and ni divides n. To start with, we're going to consider that there are numbers which don't have a prime factor. Then we're going to consider a set S of these numbers. If we can show that this set S of numbers without prime factors has no elements in it, then clearly we've shown that there are no numbers that don't have a prime factor. So, if we look at the elements of S, we're going to use the well-ordering principle, which states that a set of natural numbers, which is non-empty, must have a smallest element in it. So, let n0, which is an element of S, and n0 is greater than 1, because we've assumed that all elements in S are greater than 1, be the least element of S. Next, if n0 is prime, then it has a prime factor, which is just itself, and then it shouldn't be in the set S, because we defined S to only contain numbers which are natural numbers greater than 1 and have no prime factors. So n0 must not be prime. However, if n0 isn't prime, then we can decompose it into some factors. There exists n1 and n2, which are elements of the natural numbers, such that n0 equals n1 times n2, and n1 and n2 are bigger than 1, but smaller than n0. Now, we defined n0 to be the smallest element of S, and so n1 and n2 cannot be in S. Now, if they're not in S, that would mean that they are divisible by a prime. But any prime number that divides n1 or n2 will also divide n0, so n0 is divisible by a prime, so it can't actually be in S. So we've shown that any least element of the set S cannot actually be in S. So this implies that the set S must be empty. So that means there are no numbers, natural numbers, which are greater than 1, which are not divisible by a prime, i.e. all natural numbers greater than 1 are divisible by a prime, and as such, we have proved the theorem.